Welcome, everyone. We're just waiting for a few more folks to join us, and we'll get started shortly. Oh, Lauren, what do you think? Should we give it another couple of minutes?
Well, we have 20 folks on and 45 registered, but I think people will continue to trickle in as well. So up to you and David.
Give it one more minute. Oh, I see Elizabeth Reinhardt has joined us. Now we can actually start. Thumbs up from Elizabeth. Okay. Well, I think we will start. I'm always hoping to see folks able to come in as we go. And I don't think we're going to do introductions today. It might be nice, though, for all of you, if you'd be willing just to pop in the chat who you are and what you do so everyone can see that. My name is Marty Koistra. I work for the Housing Development Consortium, and Lauren Tierney, our Director of Member Services, is here with us helping guide us through this process today. We have an hour, and we're pleased that David Reddy has once again stepped up to take us through the vast majority of the technical content here, which we're going to get into in just a minute. So just to note, this is one of a series of workshops that we're doing on practices necessary for exemplary building and so forth. And welcome, Bill Singer. Thank you for being the first to kick us off. Sandra's following right behind. All right, David, could we have the next slide, please?
Yep, hold on, sorry.
Yeah.
There we go.
So what we want to do today is talk a little bit about why we're doing these workshops for those of you who haven't been a part of this and make sure that's clear. And then we're going to give you the high-level results that came out of the charrette we just did on this topic. And, you know, really let you know where we're headed. We haven't written the guidelines document yet for this particular topic. It is in process, but this is the most recent charrette we've had, so we don't have enough time to get it all into the format yet. But the content that you'll see today is available on the website, the Exemplary Building website, in PowerPoint form at this point. So 2 more coming up. Early integrative design is next week, I believe, the 19th, noon to 1. And then finally, balanced ventilation and heat recovery. And I did see this morning the team doing the EID, the guidelines, has a draft. So we may see that document in some form next week, along with a presentation similar to this. So again, you have to register for these events. Lauren, I think we're at this point where we'd like to do a poll. If you think you're okay with that, well, she's one step ahead of me. There it is on your screen. Please go ahead and fill out the poll. We'll give it a few minutes for the 26 participants to fill it out, and then we'll show you the results. So 3 questions. One of them is not whether or not you are a Republican, Democrat, or independent.
We're nearly there.
Nearly there, she says. All right, let us know, Lauren, when you want to cut it off and give us the results.
All right, I'm going to go ahead and end polling, and I'll share with you all.
We have been blessed with many architects today, and some developers, consultants, and some others. And looks like we are definitely headed into a space where more and more people are going to be considering the use of new approaches to domestic hot water. So timely topics. Thank you. And for those of you who hang around with us, we'll be polling you again at the end of this Zoom experience. Next slide, please. So the Exemplary Building Task Force has been busy doing these promising practices. Why and how, we'll get into in just a minute, but we have an interdisciplinary team, HDC, with Lauren's help is coordinating all of this. They have a broad scope and great depth of experience in design and development. And we're trying to eliminate that traditional cost trade-off between energy performance and unit number. In other words, we don't like being this a forced choice. We think that we can do both. And I know that means that we all have to dig deeper, so to speak, to make that happen. But we think it is possible. And we are doing 4 or soon 5 demonstration projects using some of these new strategies. So those are open source projects, which means all the data that we can extract out of them, all the learning, good and bad, becomes public knowledge on the Exemplary Buildings website. So next slide, please. So we are also saying to you, even if you're not part of the Exemplary Building pilot effort, demonstration projects, we think that all of these promising practices will be valuable, especially as we look at the 2018 Building and Energy Code becoming a reality in this environment. And next slide, please. So David, I'm about to hand it off to you. We're going to focus on domestic hot water system design today. And I just want everybody to know today is intended to be an appetizer. The entree will come when we finish the guidelines, and next year we are planning to do a whole bunch of deeper dives, more extensive dives into some of the details that you'll hear about today. So lots of topics coming at you. And David, once again, thank you so much for all your time and energy on this, and all the people who are supporting you, which I'm sure you'll probably acknowledge. Take it away. Thank you.
Yeah, thank you, Marty. Good afternoon, everybody. We have a lot to get through today, and I'll do my best. We're going to be talking about water benchmarking, fixture specifications, submetering, distribution design, and then ultimately hot water. This whole effort really started with focus on hot water, but as we got into it more, we realized that there are a number of other topics that weren't very well addressed related to hot water systems. So we ended up taking on, I think, a lot more than we planned, but we are hoping that I think it's really important work, and try and cover it all as best I can. So just to acknowledge, what I'm presenting today is not actually stuff that I pulled together. A number of people worked together diligently over a course of about 2 months. Steve Gelb from Emerald Cities, Kelly O'Rourke and Melissa Lebo from SPU helped with fixture recommendations and background on submetering. Gary Klein from Gary Klein and Associates put together an amazing deck of information about hot water distribution design. And then from Ecotope, Sean Oram and John Heller here pictured to the left. Actually, no, I'm kidding. Those are my kids, Tarek and Sean, who are single-handedly responsible for increasing our hot water and water use quite dramatically in the last couple of years. So hopefully everybody hang on for the ride. We have a lot to get through. So just kind of to set the background, what are the motivators, at least in the group's mind, of why this is really important? And first and foremost, just thinking about our goals locally and our commitments at the state level in particular, and the city, to reducing energy use in buildings. And this shows, I think a lot of people at this point have seen this chart, which shows our statewide goals for energy reduction in buildings. A 70% reduction since 2006 is the goal. We're currently a little off track in the commercial building sector, which includes multifamily buildings over four stories and above. And this is kind of drilling into that a little bit closer. You can see we're not quite on track, and really to get there, one of the most important pieces of it will be reducing our hot water energy use. This shows the breakdown of energy use roughly for a lot of multifamily buildings, and that orange bar is water heating. And we have the technology today even to make this kind of reduction, roughly cut it by a third of what it is today, primarily using heat pumps, but also focusing on design of the distribution systems, monitoring the consumption. So they're all very much connected and important to our goals. A couple other points that are that we felt our water distribution systems, the design and optimization of them is a big missed opportunity. We talk about heat pumps, but we don't talk about the piping as much as we all felt we should. And we're trying to put together some recommended practices moving forward. I still find that there's not a real concise set of recommendations for water efficient fixtures. We all are familiar with low flow shower heads and different toilets, but we're still, I think, we tried to assemble as a group a real solid set of recommendations teams can take forth. And lastly, we all probably are aware that a lot of affordable housing or housing in general aren't necessarily monitoring and billing tenants for water consumption. And this really is a missed opportunity for controlling costs. Even if you don't actually use that data to bill tenants, just having the data to be able to understand who your highest users are, so you can work with them and try and educate them on how to conserve. So jumping right in to water benchmarking, and why is this important is, I think a lot of buildings actually today have metering systems in them, but they're not utilized to what they can be in many cases. And if you can't measure it, you can't manage it. And I think this is a familiar idea that we all have heard. And what does that mean, really? What are these numbers that we're talking about when we talk about water consumption? The benchmarks are generally going to be a number of gallons per resident per day, or a number of gallons per bedroom per day. And the difference between the two is most people understand, but when we say per resident, we actually mean the actual number of residents in the building, which is sometimes hard to quantify. And so the number of bedrooms is an easier one to correlate to. But we do also find across the different building types, and we've identified the group working on these guidelines identified at least 4 different major categories: workforce, affordable housing, senior housing, family housing, so generally a building with larger units and more families, and then some permanent supportive housing. The metrics make a difference. This is an example of just how you take the same amount of water consumed in these buildings, in this case from Bellwether and Plymouth's portfolios, and normalize them to either number of residents or number of bedrooms. And you can see that the metrics can differ by quite a bit. So moving forward, we want to encourage folks to use the preferred metric, which is number of residents, which does take the effort to track the number of residents in buildings. And then, but the alternates, as we mentioned, being number of bedrooms or normalizing it by condition square footage. And ultimately, we want to have in the guidelines a set of water benchmarking recommendations, which, these are ones that I think everybody aspires to do and would do if they had the resources. But, as much as possible, we're going to try and give people the information needed to kind of do this well. What are the things to be accounted for so people don't have to start from scratch? And our work was primarily informed by two case studies, one for DSC, who uses water metering, who doesn't charge their tenants for water either, and also SHA, which they do have sort of a billing system in place. So those case studies are included in the guideline, will be included in the guidelines in the full deck, but they basically both arrive at similar conclusions, which we can talk about in the next sections here. We'll get to submetering. For fixture specifications, Seattle Public Utilities, Kelly and Melissa, primarily Kelly O'Rourke, really dug into the exemplary buildings specifications, which were pretty loose. They were basically just to install the most energy and water efficient appliances and fixtures available, or to meet the new current energy code. But those are too vague for the exemplary building task force preference, and not that clear and concise. So what she did was she put together a really nice table of concise standards for each of the different fixture types that are commonly used, including even getting into recommending when in-unit washers and dishwashers really are expected to be the most efficient choice and best complement to the unit type. Kind of focusing on larger units, having more people, and that's where using these appliances is efficient and makes more sense. So this table and the kind of background that goes into the fixture recommendations will be included in the workshop slide deck, which is available, and also we'll get into the guidelines as much as possible. For submetering, as I mentioned, this feeds back into the benchmarking effort that we talked about. You are required right now to have some level of submetering for central hot water systems. But what we're seeing is that the best systems are the ones that are measuring both hot and cold, the total water for apartments, but also are actually being used and have useful ways to visualize the data, and also even alert managers without having to go in and analyze the data, but actually have it send you an email, for example, to send when there's a high consumption event or a leak or a number of different criteria. And we looked primarily at two case studies, one by DSC and SHA, both are using submetering to locate leaks and high consumption events and try and quickly address them as quickly as possible. In the case of SHA, their metering system was, would identify leaks with the next day or over a course of days, and primarily like toilet leaks and smaller, not high use events, but over time they add up. Whereas DSC has examples of tenants that will use a lot of water in a very short amount of time, and even cause floods in some cases. So in that case, the metering system needs to give an alert within, say, 15 minutes as being their criteria. So, but in both cases, they're also using these metering systems to work with tenants to reduce their consumption. And in the case of SHA, they're using the metering systems to pass on cost to tenants, or at least provide an incentive or a penalty for exceeding a certain threshold. The metering systems have been really useful for identifying things or quantifying things that people either suspected or just seeing their overall water bills there was a problem, but they weren't really quite sure where it was. And this is example. This shows a distribution of hot water use between hot and cold for a permanent supportive housing project. And the conclusion, the data really clearly shows that roughly 40% of the water consumption can be attributed to a small number of tenants. And so once you know who those tenants are with these metering systems, you can work with them as much as possible to try and get them to conserve. And overall, this results in arriving at our recommendation, which is to provide hot and cold water metering at the unit level. We looked at, for example, doing rough-in for water meters, what the costs are of that. And if you're ultimately going to put in the meters, just doing rough-in when you're building a new building, it actually is going to cost more overall to have to put the meters in later, to commission the system later. So we really do recommend this being done from the beginning, and that they have the remote reading capability, obviously the automated reporting of high water use. That's really critical, because if you, for example, aren't looking at this data until every 6 months or after the end of the year, you can't go back and address those issues. So you need alerts, and then ultimately, when the meter's not working properly, you need an alert of that as well. Moving into the water distribution design and sizing, and this is where Sean Oram and Gary Klein put together a ton of really great information that was really comprised of 10 topics or chapters that went into a ton of granularity on the approach to, what do you need to account for and think about when you start laying out your building, even in schematic phase. What are the considerations for optimizing your plumbing distribution design? And we're not going to go through as in-depth as we did in the work charrette, but the guidelines, as best we can, we'll try and summarize this approach. And I felt that the best way to kind of summarize this was just thinking about your layout of piping in the building as being the goal of reducing both the total amount of length of piping and the size of that piping. It seems pretty intuitive that should be a good goal and that should just normally happen. But unfortunately, if you just give a set of plans to a plumbing engineer, they're going to put piping wherever they can, rather than it being accounted for in the actual layout of units. that you're not often going to hear, at least in my experience, plumbing engineers saying, hey, can you make these changes to make our piping system more efficient? Sometimes that information comes, but if we can get everybody understanding it's how important it is. And this kind of summarizes, just in terms of sizing a system, a couple different approaches. And this gets to what almost ultimately translates to: what is the size of the pipe that you need connected to the water main in the street or the building, based on the assumptions of demand. And what a lot of engineers have been using are what I would consider antiquated methods, because that are based on assumptions for fixtures that at one time existed, 5 gallon per flush toilets, or 2.5 gallon per minute faucets for lavatories and all around. There's things with low flow fixtures, just that's not the case. And the sizing methods, until recently, haven't really accounted for that very well. And this just goes to show that under the different sizing methods, GPM being the gallons per minute peak flow, using for the same building, using 4 different methods, ranges from 260 gallons per minute to 54 gallons per minute for a building in Seattle. And that translates to the difference between a 4-inch plumbing main, domestic water main from the utility, versus a 2-inch. And that's a pretty dramatic difference. And that difference in assumption of peak demand trickles through all of the piping systems. And so that your mains get smaller, your branches get smaller, and twigs, etc. So it really does reduce the plumbing material cost, the plumbing labor cost, hopefully, and also your connection fees. And people, I think, may be skeptical. Some engineers may be skeptical that can we rely on these design assumptions? And fortunately, there's a ton of data like people like Gary and Ecotop have assembled on actual peak flow draws. These are hot water draws, but the data does suggest that even the most aggressive methodology, the most current methodology that accounts for low flow fixtures, is still very conservative, even when you look at actual fixture or actual building peak demands. So I think the conclusion is everybody should feel comfortable using these new methods for sizing, and also the exemplary building task force and people like Gary Klein are working with authorities that review these designs to make sure they understand it and buy off on it. So there's a huge opportunity here, just not only in piping, but even just your connection fees with utilities and your monthly costs. This is just a comparison between Seattle Public Utilities and a project I'm working on, Skagit, that is in Skagit County, and how dramatically different, depending on what jurisdiction what utility you're working with, how big of a difference in connection fees. In Seattle, a connection fee might be $20,000, but in Skagit, it's $40,000. And these numbers really inflate as you go up into larger pipes connections. And then the monthly base charges as well. So potentially saving hundreds of dollars every month on your water utility costs. So I think of all the things that I learned in doing this charrette, that the opportunity for reducing pipes and how they trickle through to cost reductions and utility costs, connection fees, and monthly charges, that was the biggest thing that I took away from it. As we move into the building itself, there's two, when we think of hot water optimization of the distribution system, we kind of need to understand that there's two there's two primary, there's the energy you need to heat the hot water as if you were taking it right out of the water heater. And then there's the heat that you lose just pumping that water through a building 24/7, 365 for the life of the building. And what I think a lot of people don't realize is that the amount of energy used just for heating hot water is, say, 15 to 20% of building energy use for multifamily. But there's another 5 to 10% of total building energy use that is just to keep that water hot and recirculating. So there's a tremendous opportunity for reducing the building's energy use just by reducing this circulation load, as we call it, or temperature maintenance load, to keep the pipes hot. This phenomenon has been measured. What we know is that there's a huge variation in actual buildings, how much is lost through that distribution unit, distribution system, and it's very hard to predict because the models of the distribution losses are based on assumptions of that the piping is installed as it was laid out, and then also that it was insulated as you would assume it would be to meet code. And what we know from just measuring the losses and even inspections is that's not always the case. Insulation there's gaps in the insulation. There's just complete, some buildings, even though it might be in a spec or on a drawing, there's just no insulation. So it's one of those things that, again, is a huge opportunity if it's just properly specified and inspected to be installed. And then getting to, there's the insulation of the pipes, but there's also just the layout of the piping, as we talked about earlier, and how you choose to lay out the piping. If you assume that it's distributed from the water heater and that every single apartment has its own stack, you can just see all these little red lines. Those are all radiators of energy into your building. And if you can consolidate those risers to one for every stack of 2 units, then you can quite literally cut the piping in half, potentially. It's not always going to be the case, but it should be a goal of every project to strive to consolidate the number of risers as much as possible. How does that translate to? Just reducing, just optimizing the piping can save roughly half of that losses, and then properly insulating really cuts that again in half as well. So these are calculated values, but assuming the system is installed and insulated as assumed in the calculations, the team agrees that achieving this very low metric of 28 watts per apartment, and that's one way we've decided to kind of quantify that number, is watts per apartment. You can think of it as how many light bulbs equivalent of energy is lost from this distribution system per apartment, and we can reduce that by anywhere from 150 to 25% to 20. I'm sorry, losses can be reduced to roughly a quarter of what they are being measured today. And how do we do that? I mentioned the reduction in piping, but also the attention to details on the insulation itself, properly isolating the piping. This shows some examples of that, and then inspection of the final product before everything's hidden behind drywall and shafts. So in summary, this being, I think, really one of the most important parts of the effort that was put into this is focusing on optimization of the distribution design, and then using to achieve the sizing that I described for the peak flow, using what's called Appendix M in the 2018 UPC. Sorry for missing that in this slide, but it's a methodology that is part of the plumbing code as of 2018, formerly part of the 2018 UPC, and is currently used and accepted, at least here in King County, for sizing peak demand. And then lastly, attention to the insulation details. So last but not least is the domestic hot water plant design, which again is kind of where we all thought this was going to focus, but ended up being a smaller but still very important component of the overall guidelines. And the considerations that go into designing hot water systems that use electric heat pumps are there's a number to keep in mind, and that engineers are getting a better and better understanding of them, what's important. And a lot of that is attributed to Ecotope's work, developing these systems over the last 10 years, and utilities supporting that effort. And today we are at, in my opinion, the point where this can be commonplace, but it's only for a few reasons that we're going to talk about. One of which is to just really understand how these technologies work. They're not the same as boilers. Heat pumps are not the same as boilers, and they're not all heat pumps are the same. The two main categories are what we call a single pass heat pump or multi-pass heat pump. And if you're not designing these systems, you should just the only takeaway you have is that in one case you really want cold water, as cold of water as possible coming into the heat pump. That's for the single pass. That means you need a stratified tank. But for multi-pass, that's more like a traditional boiler where you have the water coming into the heat pump can be warm or cold, and it just increases the temperature of that water by a little bit every time it runs the water through the heat pump. So most of the systems, the highest efficiency systems are expected to be the single pass type heat pumps that are now being used more and more. One thing with the single pass design that everybody should be aware of is that really we can divide it up into two pieces: the heat pump and the storage tank that hot water that the heat pump generates is stored in. That being needs to be separate from the recirculation system. And so on the left, you can see the heat pump component and the storage tank that goes with that. And then on the right side is another tank with that we call the swing tank, that is really intended to handle the recirculation losses of the building. And that could be an electric resistance heater, it could be another heat pump, but they just need to be separate with this single pass when using single pass systems. So that translates to a little bit more space required for the overall heat pump system, but it has a pretty significant improvement in the efficiency. It results in a much higher efficiency system. We talked a little bit earlier about the maintenance load. This is important again because it really plays into how big does that swing tank need to be, how much capacity does it need to be, and what is the overall peak possible efficiency of the system. So again, no matter what kind of system, whether it's a boiler system or a heat pump system, reducing temperature maintenance losses or the recirculation losses are really important to the design of the system. So once we know the loads of the building, we need to come up with what is the required volume and capacity, or the number of heat pumps needed. number and size? And those are usually the two biggest questions that I hear working with teams early on with heat pump systems is, all right, how much space do I need for these tanks, and where are we going to put the heat pumps? How many heat pumps are we talking about? And fortunately, there's been a lot of lessons learned in here, and this shows a picture of two very different heat pump systems. The one on the left being a 55-ton heat pump that requires, I'm not positive, but I'm pretty sure it's probably very high voltage, 3-phase high voltage connection, and thousands of gallons of storage, 1,000 gallons of storage. And that system actually was designed for building very similar to the one on the right, which is roughly a tenth of the capacity and half the storage. So this is just to show that the sizing of these systems wasn't real well understood when heat pumps were first being used for multifamily. But fortunately now we have the tools and the information to be able to properly size these systems. And part of that sizing is the load of how much are the occupants going to use. This is really important because you don't want to, heat pumps generally cost a little bit more per BTU capacity, and that storage goes up the higher the load assumption. So you can't just be super conservative, otherwise you're going to result in a huge heat pump water plant. And understanding when that water is used is also very important. This slide shows that in most buildings, there's a very large peak in hot water use in the morning and then also in the evening. And on an average day, that can be half of what the peak or design day might be. So we need to understand what the range is between the design condition and an average day and properly size the equipment accordingly to those loads. So one of the kind of a real common, based on a lot of submetering data I've seen, a rule of thumb is 20 gallons per person per day is the average amount of hot water used. And unfortunately, we do now, actually, as of roughly about a month ago, have a really useful and important tool at our availability to size these heat pump systems. Ecotop developed an online tool. There's the web URL at the top here to help designers size these systems using all the information they've gained over the years in their development of these. So this has been really valuable to just to be able to put in the inputs that we now have or we've talked about in these guidelines, and actually have come out of that how many gallons of storage and how many heat pumps do we need. So this is a big advancement. Most of our heat pumps are going to be using different refrigerants. There's a wide range of refrigerants that are used in these heat pumps, and the most efficient ones and the ones that perform the best in our climate, in my opinion, are the CO2 heat pumps, which are right now currently available primarily in the small sand-in heat pumps that some of you may be familiar with. But there are larger ones coming to the market, and we can plan to see CO2 heat pumps being used in anywhere from the very small buildings to the very large buildings. Unlike in the past development has kind of focused on these, what they call reverse cycle chillers, which use R134A as a refrigerant. This just kind of, when it comes to refrigerants, it's important because of the global warming potential of the refrigerants used. And the larger heat pumps historically have used the R134A refrigerant, which is much higher global warming potential than CO2, which is so this is important not just for energy performance, but also because the impact of these refrigerants getting in the atmosphere inadvertently, hopefully it would happen, but if it does, the climate impact is minimized by using the CO2 equipment. So the most familiar deployment of these central heat pumps, CO2 heat pumps, is locally the Elizabeth James retrofit project that EcoTurf did with Community Roots. And it was, in my mind, from the data I've seen, a very successful project. Demonstrated how these heat pumps and the swing tank concept perform. Some notable takeaways is that the peak draw of energy is the kW, which is important for transformer load calcs and all that, is actually pretty small. So and really 4 heat pumps was enough to heat the hot water for 60 apartments. So I think that's really one of the things that as we learn how to size and specify these systems better, we can optimize them and not oversize them as maybe has been done in the past. And the lessons learned are that we can achieve literally a 3-time increase in efficiency compared to regular electric resistance. Redundancy is really important because if you do have one heat pump getting damaged, as shown here, or just not working for whatever reason, you have backup, you have redundancy. And alarming is another. Alarming meaning if there's a problem with the system, that somebody is informed of the problem. And now there are controllers and equipment that are designed for sending an alert if there's a problem with these systems. Whereas in the past, it just had to be a call from a tenant being, well, we don't have hot water. So, as these evolve, there are some plug and play packages being developed, so to speak. So something that can be literally skidded and put into a project, and rather than being a custom design system every time. So a lot of advancement in the last, especially in the last couple of years in this area, that is really important to be aware of. One questions we get is will switching to heat pumps reduce utility costs? This shows a comparison between a natural gas condensing system, dollars per apartment per year, compared to electric and non-CO2 heat pump and CO2 heat pump. And we can see is that at current gas prices and current electric prices, you won't really see a cost savings on your utility bills switching from gas to heat pumps. But what we do know is that, especially using Seattle City Light energy, electricity, for example, there's a huge reduction in climate impact compared to gas. So, and over time, we expect that price of gas could go up, and in some ways, and you can take advantage of renewables on the grid with electric heat pumps. So it definitely is a direction that the shift is happening. And in terms of incentives, right now, until they become required by code, there are incentives, and they range from anywhere from $300 to up to potentially $800 to $900 per unit, depending on which utility you're working with. And at least for PSCs, higher incentives, you have to implement other what they call bonus measures into your design. So the numbers are not insignificant until at least they become required by code. So with that, I haven't been monitoring the comments, so I don't know, we can open it up for questions at this point.
Thank you so much, David, for walking us through that. I suspect some people are curious, some are overwhelmed, some are wondering what the heck to do with all this information.
Yeah.
But we have at least one thing that popped up early in the chat that I want to make sure we clarify. That was Stephen's point about the benchmarks are total water use, not just hot water. Do you happen to know, David?
Yes. Yeah, and in my experience, it's roughly a 50-50 split between hot and cold. So those benchmarks on the slide, I think they were, anywhere from 50 to 70 gallons per person. That's you can just split those numbers in half between hot and cold.
Super. Well, I think we should let people just come off of mute if you want to ask a question, otherwise pop it in the chat. And of course, for those of you who are shy, you know that I'm not afraid to call on people either. So,
Marty, this is Gary. I do have
Yeah.
a follow-on question to the one that was just discussed. If I remember correctly, David, the note there was showing that the benchmarks were for not necessarily water efficient fixtures and appliances.
Yeah,
They were for what it was ever in the building.
that's right.
So we should expect that if they're using more efficient stuff, the benchmarks would go down,
Yeah.
at least some.
Yep. Yeah, and the numbers that I having benchmarking a few ESDS buildings, which, as most people know, ESDS does have some historically more stringent water efficiency standards than code. So already using low flow fixtures, I see those numbers being roughly 20 gallons per person of hot and 20 gallons of cold per person as being kind of benchmarks.
Interesting you say that. I did other calculations a few years ago to estimate what it would be following California code, which is arguably more stringent than much of the country. And I came up with 40 gallons per person per day too, as a good estimate.
Yeah.
For total water use.
Yeah, ESDS has kind of been in line with what California has been requiring, at least recently. And as I think Washington did adopt California's water efficiency standards recently as well. So we should see that being kind of the normal, although even in market rate and, low flow fixture costs are generally not a huge increment. So it's becoming almost universal.
When you specify the aerator at the time of purchase of the building, it's 0.
Right.
So I'd say that's a small increment.
Yeah.
And then, toilets are competitive. So what are we left with? Washing machines and dishwashers, right?
Mm-hmm.
And again, I'm pretty sure that the more efficient stuff is roughly competitive with the regular stuff, particularly if you start specifying lots of it. So, but it's interesting to hear that the metric is on the order of 40 gallons per person per day, split half hot, half cold. Those are reasonable numbers. I think the hot's a little high. I think it's closer to 15. And it depends if you're counting the washing machines as being in the apartment or not in the apartment. But it's in the right ballpark, that's for sure.
No, that's a good point about the appliances that are involved, whether laundry specific being one of the bigger ones.
Other questions from folks, comments, things you want clarified?
This is John Hall. Just wanted to comment about the plant sizing you were talking about, and reading the tea leaves that gas systems may be very soon not permissible at least in the city of Seattle. And so while the utility cost savings may be nominal, as you pointed out, the carbon savings is huge. But pretty soon we're not going to be allowed to even probably use gas moving forward. So
yeah, the 2018 Seattle Energy Code requires heat pumps or use of heat pump for central water heating. And just to meet those goals at the state level, I think we're headed in the same direction at the state level as well.
So this is Alistair, O'Brien 360, and just want to commend everybody on an awesome presentation. I'm sorry I've not been able to be as involved in this hot water conversation as I would have liked. But I'll take the opportunity just to call out how, you know, this very much speaks to this whole idea of integrative process and integrative design. And yet again, you know, as we've seen so many times with the exemplary building program, there really is some tremendous potential from really thinking about goals early and figuring out how to blend architecture and engineering to really optimize performance. So, you know, I'll beat my little evergreen drum one more time that really trying to leverage the idea of integrative process is sort of super critical at this point. But nice job, everybody. I thought really excellent, some really good slides. I think in terms of kind of helping to illustrate the issues to project teams, there's some really good material here, which is cool.
Yeah, and appreciate that, Alistair. It's certainly there was so much content assembled for the charrette, and I feel like I didn't give it as much justice as it deserves. I hope the guidelines will be our best effort to consolidate and distill it as much as possible. But yeah, absolutely, the integrative process that became more apparent as we all work together on this is just how getting this out in front of everybody early is critical to the adoption.
Appreciate all those comments, and I'm going to pick on Mindy Black in a minute, but I think Lauren's getting ready to pop up our last poll. We're almost out of time. Mindy, as a developer, any thoughts that you have about all of this?
We're definitely looking at how to actually eliminate gas from all our projects. So tracking closely the upcoming release of new technology relative to the heat pumps. I understand there's one on the horizon that all of our engineers want to design around, but it doesn't have UL listing. So hopefully we can get out of politics, back to getting work done, and move forward with some really great projects. And I love the sharing the Ecotope did with their calculator. I actually clipped that link and sent it on to my engineers.
Super. Thank you, Mindy.
Marty, this is Emily. Can I just chime in real quick?
You can, and I see Lauren's got the poll up while you're talking.
Yeah, so I guess I would just say I've had some conversations with David about this as well, and I think to sort of close the loop full circle here a little bit from the development side versus the engineering side and why this is the right thing to do. As developers in an environment of scarce resources, we are always thinking about how to maximize scoring. And one of the challenges previously had been to maximize the hot water heating score for the C406A table. The solar thermal system is phenomenally the solar thermal water heating system is phenomenally expensive. And so as David pointed out, this is a much more cost-effective way to create the same energy savings to the building and get that point. And the points are changing anyway with the energy code changes. But so this will help buildings to make choices for the right dollar, for much less dollars, and still get the points.
Super. Thank you for pointing that out, Emily. And Lauren, do we have the results? Aha. Well, thank you all for participating and for those scores today. This presentation has been recorded. There's also a transcript available at Otter Live Notes that we can make available to folks if they need it. This information will continue to go on the EBP website, along with, as David referenced, the guidelines, which will take us one step closer. I want to thank the team again for all their hard work. Many, many, many hours went into all of this. And David, fine job on synthesizing and portraying it. Lauren, as always, for getting us together, and good to see all of you. Stay safe out there. We know that the virus is pressing in on us from all directions. Let's be smart, wear our masks. Thanks. Take care now.
Thanks, Marty.
Thanks.